In section 6, we're going to shift gears here from transformations and look at some this idea of identifying symmetry. Okay, and I think this is an idea that you've already been introduced to, and hopefully this is more of a review for most of you than anything else. So, the first type of symmetry we're going to talk about is reflection symmetry or line symmetry. Okay, and reflection or line symmetry simply means how many ways can we cut this thing in half. So if you have a rectangle, and it probably should have marked this figure a little bit more specifically and make sure we know it's a rectangle. So if I know it's a rectangle, then I think we all agree we can cut this thing in half by going straight up and down or by going from left to right. Some of you might be saying, well, why can't we go this way diagonally? Okay, well, it should make sense if you see this. If you picture a piece of paper and you try to fold this top part right here down over when you reflect it, okay, it's going to end up coming out down this way in this direction, okay, and that would be the reflection there. So, again, excuse me, if you have your doubts, very simply take a piece of paper and try to fold it diagonally, and you'll notice that it doesn't work out. Okay, now part B here, and again, this is still a little bit sloppy because we should say it's a regular pentagon, but nonetheless, this thing has a few lines of symmetry. Okay, the first one I think we all see plain as day can go right down the middle. Okay, now if you look on more of an angle, you should be able to see that you could also cut it in half this way, and you can also cut it in half this way. You can also cut it in half this way, and the last one is you can cut it in half that way. Okay, so in this particular problem, there are 1, 2, 3, 4, 5 different lines of symmetry. And the reason I didn't count this one right here is because it's obviously already been counted. That was the first one. So there are 5 lines of symmetry in the pentagon, in a regular pentagon. Okay. Moving forward here, part C does not look like a regular polygon, so we will assume it's not. So the only way to fold this thing in half or cut it in half would be to go straight down the middle there. And that would be the only way to cut that in half, so that would be the only line of symmetry there. Okay. Again, part D, this is a little bit sloppy here. I apologize for not labeling these a little bit better, but let's just assume that this guy is an isosceles trapezoid. Okay, in the event it's an isosceles trapezoid, well then you have the ability then to draw a line of symmetry right down the middle, and that would cut the figure right in half. Okay, and then lastly, let's go ahead and say that this thing is a square. Okay, so we'll do that, mark it up like it's a square, and now I look at the lines of symmetry. I could go here. Now with the square, I can go through the diagonals. Okay, I can go through these sides, I can go through this diagonal. And so I think we're good there. All right, so this thing would have 1, 2, 3, 4 lines of symmetry. Okay. One thing to note here, when we call it lines of symmetry, it's also a line of reflection. Okay, so if you look at one, it essentially cuts it in half, so you could have reflected over that line, and that would have been fine. Okay, so this idea of rotational symmetry is probably more new to you. Very simply, if you can take a figure and you can turn it, all right, and at some point it's going to land back on itself of 180 degrees or less, then it has rotational symmetry. So if I look at the square, okay, so we'll mark it up. If I take this figure, and here's the center point, if I just start rotating each vertex in this direction, okay, and I just start spinning this shape, eventually I'm going to end up right back where I started, okay? Because eventually point A is going to be where point B is, and point B is going to be where point C is, and point C is going to be where point D is, and point D is going to replace point A. And when all of that happens, it's going to be a we're going to know that it does have rotational symmetry, okay? So the square has rotational symmetry. The center is the intersection of the diagonals, blah blah blah, okay? So how much do I have to rotate the square to get it back onto itself? Well, I just got to go a corner turn, and so a quarter turn is just telling me that, hey, 90 degrees is the angle of rotation here. Okay, we could have known that also because this says right here, 360 divided by the number of lines of symmetry gives you your rotational symmetry. So if you remember from the example above, a square has 1, 2, 3, 4 lines of symmetry, 360 divided by 4, that's where that 90 came from. Okay, so that's more of a systematic way of finding the degree of rotation. So a regular hexagon, so it does have rotational symmetry. If I look at a regular hexagon, the only way I can cut this thing in half is I can go vertically this way, I can go horizontally that way. Okay, that's the only way I can do it. There's no other way to cut this thing in half. Okay, and so I have 2 lines of symmetry, so 360 divided by 2 tells me that the degree of rotation here is 180. Okay, so I just take it, I rotate it 180 degrees about the center point here, and I end up right back where I started. So when we talk about rotational symmetry, that's all we're saying is keep rotating until you're going to end up with the same exact figure you started with. All right. So again, rotational symmetry. Well, a kite has 1 line of symmetry. Okay, that's it. So 360 divided by 1 is 360. But every figure has 360 rotational symmetry because when you rotate 360, you end up right back where you started. So a kite does not have rotational symmetry because no rotation of 180 degrees or less maps it onto itself, right? We said 360, so that's not going to work out. Okay. What about this dodecagon? Let's look at the dodecagon. So I can cut it in half. Let's see. I can go this way and this way for sure. 1, 2. I'm pretty sure we can go through these. So 3, 4. I'm thinking that's about it. Okay, so we have 4 lines of symmetry, so it has rotational symmetry because we know 360 divided by 4 tells us that the angle of rotation would be 90 degrees. Okay, and then finally the last 2 examples, I'm hoping that this is coming pretty easy to you. And again, you might want to pause the video and kind of work through these on your own. But so this first guy has 1, 2 lines of symmetry, so we have 360 divided by 2. So this thing does have rotational symmetry 180 degrees. And then the last one, this one looks a little bit more interesting. Let's see here. So we can go 1, 2, 3, 4. Let's see here. 5, 6, 7, 8. So we have 8 lines of symmetry there. I know there's a lot going on there, but so we have 8 lines of symmetry. So 360 divided by 8 is going to give us 45 degrees. Okay, so rotation of 45 degrees will map this shape back onto itself. So again, that's just a quick summary of what it means to have lines of symmetry and what it means to have rotational symmetry. So as always, questions, have them ready tomorrow, and we'll go from there.